Solid state. We all know that matter exists in three states. These are solids, liquids, and gases. They differ in the interparticle spaces, which are least in the solid state and maximum in the gaseous state of a substance. Among these three states, the solid state is the most important state. Here we will study the basic definitions and the types of crystalline solids. The question arises, why only solids? Out of the known elements, 11 exist as gases, 2 as liquids, while the rest are solids. We are all surrounded by a variety of solid objects which differ in size, shape, and also in mass. The metals are the backbone of our industry. With the exception of mercury, all the other metals are solids. Most elements are solid at room temperature. The atoms are approximately in their fixed positions. Simple case is a crystalline solid. The solids differ from the other two states of matter in rigidity and fluidity. Apart from these, solids differ with respect to density, melting point, boiling point, luster, electric conductivity, and thermal conductivity. All these characteristics are mainly because of extremely close packed structures in the solid state. In the present unit, we shall focus mainly on the crystalline solids because most of the solids are of crystalline nature, although amorphous solids are also quite common. Crystals are everywhere. We can see crystals. More crystals. A large number of naturally occurring solids exist as crystals. Few common examples are of sodium chloride, copper sulfate, diamond, sulfur, sugar, etc. The early ideas. Crystals are solids, but solids are not necessarily crystalline. Crystals have symmetry as said by Kepler and have long range order. Spheres and small spheres can be packed to produce regular species. Let us now see whether the early ideas were up to the mark or there is a difference in the exact packaging of these closed crystalline structures. Before starting the crystalline solids and their structures, we have to know the characteristics of the solid state. All solids have definite mass, volume, and shape. Their intermolecular distances are very short. The constituent particles have fixed positions and can only oscillate about their mean positions. They are incompressible and rigid. Apart from these, the solids maintain their volume independent of the size and shape of the container in which they are placed. They are almost incompressible and have high density. Solids have negligible fluidity as compared to liquids and gases. The diffusion of the particles in the solid state is also negligible. Solids. A solid may be defined as a form of matter in which the constituting particles, that can be ions, atoms, or molecules, are closely packed and held so strongly that they cannot easily move past each other. As a result, this form of matter has definite shape as well as a definite volume. The solids can be classified broadly into two types. These are crystalline solids and amorphous solids. In the crystalline solids, we will find that these are the solids in which the constituent particles have a regular orderly arrangement throughout, and it gets repeated again and again, resulting in a definite pattern. We can also say that these solids have long range order and the particles are in highly ordered arrangement. The other type of solid is that of amorphous solids, and these are the solids in which the constituent particles do not possess the regular arrangement throughout. As a result, the amorphous solids have irregular shapes. However, in some cases, they may have small regions of orderly arrangement in which they behave like crystalline solids. Such regions are called crystallates, and thus the amorphous solids have a short range order and there is no particular order in the arrangement of the particles. Differentiating between the amorphous and crystalline solids, it has been found that the crystalline solids are of long range order whereas amorphous solids are of short range order. Sodium chloride and quartz are the typical examples of crystalline solids, whereas examples of amorphous solids include glass, rubber, and plastics. Crystalline solids are found to have sharp melting points, whereas amorphous solids are found to have a range of melting points. That is, when they melt, they gradually soften over a wide range of temperature. The structure of amorphous solids is similar to that of the liquids. All the crystalline solids are not ionic. Example, in diamond and quartz, the constituent particles are held by covalent bonds and the attractive forces are covalent bond forces. Similarly, electrostatic attraction is also present in the constituent of the metals and van der Waals forces in solids like iodine, sulfur, etc. Crystalline solids are also known as true solids, whereas in the case of amorphous solids, they are regarded as pseudo-solids since they are not true solids. For example, glass and pitch. Certain amorphous solids are also known as supercooled liquids. On heating amorphous solids, it becomes crystalline at some temperature. Example, some glass objects from ancient civilization are found to become milky in appearance because of some crystallization. Also, we found that a glass which softens upon heating due to certain temperature, it may behave like fluid. We often find that glass panes fixed in the windows or doors of old buildings are found to be somewhat thicker at the bottom than at the top. It actually slowly flows down with the changing temperature conditions, and as a result the bottom portion becomes thicker. In fact, due to continuous heating in the day and cooling at night, glass acquires somewhat crystalline characteristic. This is also called as annealing of glass. Now we know why window panes are thicker at the bottom. Crystalline solids are anisotropic. Now what is anisotropy? The substances which have the properties such as electrical conductivity, thermal conductivity, mechanical strength, refractive index, different in different directions are regarded as anisotropic substances. That is, here also the crystalline solids are anisotropic because they don't have these properties same in different directions. Some of their physical properties like electrical resistance or refractive index show different values when measured along different directions in some crystals. It may be noted that the crystalline solids are anisotropic because in making measurements in different directions, the particles which fall on the way are not the same. Like as shown from moving A to B, the particles are not the same as while moving from C to D. Amorphous solids, on the other hand, are isotropic and their properties remain the same. Now, the properties comparison. Crystalline solids, as known, have a definite characteristic geometrical shape, not like that of the irregular shape of the amorphous solids. Crystalline solids melt at a sharp temperature. Amorphous solids gradually soften over a range of temperature. It has been also found that when a crystalline solid is cut with a sharp-edged tool, it split into two pieces and the newly generated surfaces are plain and smooth. Whereas in case of amorphous solids, when cut with a sharp-edged tool, they cut into two pieces with irregular surfaces. Crystalline solids have definite and characteristic heat of fusion, whereas amorphous solids don't. Crystalline solids are anisotropic, amorphous are isotropic, and they are therefore true solids, and amorphous solids are isotropic in nature. In considering their order in the arrangement of the constituent particles, it has been found that crystalline solids are of long range order, whereas amorphous solids are only short range order. Up till now, we have discussed in detail the two main types of solids, that is crystalline and amorphous solids. Please note that the majority of the solids which we come across are of crystalline nature. These may be metals like copper, silver, gold, etc., or non-metallic elements such as sulfur, diamond, phosphorus, iodine, etc., or ionic solids such as copper sulfate, sodium chloride, zinc sulfate, etc. Crystalline solids have been classified into four categories depending on the nature of interatomic, or we can say ionic or intermolecular forces which operate. These are ionic, metallic solids, covalent, and molecular solids. We are here giving a brief description of different types of crystalline solids. Ionic solids. Ionic solids have the constituent particles, basically the ions, and the bonding or attractive forces occurring between them are the Coulombic or electrostatic forces. The ionic solids, as they are made up of oppositely charged ions, that is cations and anions, closely packed in space. Thus, the anionic solids have a three-dimensional space or representation of the constituents in space. Ionic solids have closed packed structures in which the cations and anions have strong electrostatic forces of attraction. These may also be called as ion-ion interaction forces. Examples are that of sodium chloride, magnesium oxide, etc. Physically, they are hard but brittle. They are insulators in the solid state, but they can conduct electricity in their molten as well as in their aqueous solutions. They are found to have high melting point. Coming to the metallic solids, about 3/4 of the known elements are metals, with the exception of mercury and gallium, which are liquids. All other metals are solids. They are quite hard, have high melting points, high electrical and thermal conductivity. They are also malleable and ductile. In metallic solids, the constituent particles are the positive ions in a sea of delocalized electrons. Now, positive ions are what? These are the constituent particles, are the atoms belonging to the same element. They are linked by metallic bonds, and actually each metal atom is supposed to consist of the two constituents. These are mobile valence electrons and the positively charged residues called as kernels. And the simultaneous attraction between these valence electrons and the kernels belonging to a large number of atoms placed side by side in space results in the formation of the metallic bonds. Example is that of iron, copper, magnesium. They are hard but malleable and ductile, and their melting point is fairly high. Coming to the next are the molecular solids. In molecular solids, the constituent particles are molecules. Depending upon the nature of these, the molecular solids have been classified into three types. First are the non-polar molecular solids. The constituent particles present in the solids are discrete or independent molecules in which the atoms are linked by covalent bonds. Some of the examples are hydrogen, oxygen, nitrogen, etc. In addition to these, non-polar molecular solids also include noble gases like helium, neon, etc. Due to the absence of any charge, the attractive forces which bind the constituent particles in these solids are the weak dispersion or London forces. In order to understand the origin of London forces, we have to consider that the nuclear charge present in the center and the electrons which are located diametrically opposite to each other, their centers coincide. Thus, the helium atom, just like an example, the helium atom is completely nonpolar. But since the electrons do not have a fixed position, it is possible that at a particular instant the electronic distribution may do not remain symmetrical and the centers of the positive and negative charge may coincide, and the atoms become symmetrical again, but it will introduce a polarity on the neighboring atoms which will become induced dipolar. Two such atoms are attracted towards each other by the attractive forces known as London forces. These are physically soft and have low electrical conductivity, and their melting point is also very low. Then the polar molecular solids. As the name suggests, the constituent particles in these solids are of polar nature because of their electronegativity difference in the bonding atoms. For example, HCl or sulfur dioxide. Physically, they are soft and again insulators having low melting points. Their melting and boiling points are comparatively higher as compared to non-polar molecular solids, since the dipole-dipole interactions are comparatively more than the van der Waals forces. Because of low melting and boiling points, polar molecules exist either as liquids or gases. Coming to the hydrogen bonded molecular solids, the bonding or the attractive forces occurring in them are the hydrogen bonding. The participating atoms are highly electronegative in nature, which are linked to the hydrogen atom by covalent bonds. The polar covalent bonds are involved in strong dipolar attraction known as hydrogen bonding. The hydrogen bonding also shows the following characteristics, that is, at room temperature and under ordinary pressure they exist either as volatile solids, volatile liquids, or as soft solids because they are physically harder than the non-polar and the polar molecular solids. They are also non-conductors in nature. The molecular solids have higher melting and boiling points as compared to the other two types of solids, since the dipolar interactions involved in leading to hydrogen bonding are strong. Next type is that of the covalent solids. A covalent network solid is a solid that consists of atoms held together in large networks or chains by covalent bonds. They are very hard, have high melting point, are poor conductors of heat and electricity, and have high heats of fusion. Examples include that of the carbon in its form such as diamond or graphite, asbestos and silicon carbide. Here, the constituent particles are atoms which generally belong to nonmetals. These are linked by covalent bonds. The arrangement extends through the solid and is called as network, as shown over here. This is a network. These are therefore also called as network solids. For example, in diamond, which is a crystalline allotropic form of carbon, the constituent particles are carbon, like in this. Here, in diamond, the constituent particles are carbon atoms which are sp3 hybridized, and each carbon atom is linked tetrahedrally to 4 other carbon atoms present in the space, and this results in a three-dimensional network as shown over here. So diamond is an example of covalent network solid in which the atoms are covalently bonded to each other and have hard and high melting points. Coming to the comparison of the different type of solids, that is molecular, metallic, ionic and covalent solids, this is a general difference between the properties of the different type of solids which we have discussed already. To determine the structure of a crystalline solid, we have to study the extra diffraction pattern of it, and we have to apply the Bragg equation, which is n lambda equals to 2d sine theta, where lambda is the wavelength of the X-rays, n is an integer, d is the distance between crystal planes, theta is the angle of incidence. We will study about this Bragg equation later on in a complete detail. There is a small illustrative problem over here on the basis of Bragg's equation. The planes of a crystal are 0.281 nanometer apart and angle 2 theta is equal to 1.8 degrees. Then for first order diffraction, what is the wavelength of X-ray used? So by applying the Bragg equation, we can come to its conclusion, and the answer is 0.058.